Dominic and William each started the year by depositing $1,000 into savings accounts at their banks that each offer 4% interest rate. Even though neither of them made additional deposits, at the end of the year, Dominic had $1,040 in his account, while William had $1,040.60. How is this possible? While Dominic and William both received a 4% interest rate, the fact that they used two different banks informs us that the interest on one of their savings accounts must compound more frequently than the other. In fact, it turns out that Dominic's account only collects simple interest, while William's account has interest that compounds quarterly. Simple interest can be calculated using the formula I equals PRT, which states that the interest is equal to the principal times the annual interest rate times the number of years. Using this formula, we can find that Dominic collects $40 after 1 year, bringing his balance to $1,040. But how did William end up with 60 extra cents? Well, we know that he still gets a 4% interest rate, but his interest is calculated and paid quarterly, every 3 months. And whatever interest he gets on one quarter, he is able to gain interest on that interest in the following quarters. This is what makes compound interest so interesting. Even if William never deposits anything else into his account, his interest will continue to grow larger and larger with each quarter. While slow at first, this forms exponential growth that becomes more and more powerful over time. Let's work through the arithmetic of it. We know that William started the year with a principal of $1,000 and receives a 4% interest rate. Since his interest is compounded quarterly, he will receive a piece of that 4% interest every 3 months. At the end of the first quarter, William receives 1/4 of the 4%, which is 1% applied to his current balance of $1,000. Then this first quarter interest is added to his starting balance. So we can represent his balance at the end of the first quarter as Q1 being equal to P plus P times R over 4, or equivalently, P times 1 plus R over 4. So after the first quarter, William's balance is $1,010. What will his balance be at the end of the second quarter? To determine that amount, we want to apply the 1/4 of the 4% interest to William's newest balance, Q1. So this time, we are going to have Q2, the balance at the end of the second quarter, equal to Q1 plus interest. In other words, we can basically reuse the formula for Q1, but we are going to write Q1 in place of P now because Q1 is the new previous balance. So Q2 is equal to Q1 times 1 plus R over 4, which is equal to 1,010 times 1 plus 0.01. So Q2 is equal to 1,010 times 1.01, which is 1,020.1. This would give us a new balance of $1,020.10. Before we move on to the third quarter balance, I want to point something out. When we wrote that Q2 equals Q1 times 1 plus R over 4, we were equivalently saying that Q2 is equal to P times 1 plus R over 4 times 1 plus R over 4. Because we already defined Q1 as being equal to P times 1 plus R over 4. This expression can be slightly condensed to Q2 is equal to P times 1 plus R over 4 squared. All right, let's look at the end of the third quarter. William's balance at the end of the third quarter, Q3, should then be equal to Q2 plus interest. Since we just said that Q2 is equal to P times 1 plus R over 4 squared, we can use that in the calculation of Q3. We now have that Q3 is equal to the initial balance P times the quarterly interest cubed. Plugging in William's starting balance of $1,000 and the interest rate R equals 0.04, we get that Q3 is equal to $1,030.30. In this quarter, the interest was greater than in the previous by an increment of 10 cents. The fourth quarter balance, Q4, can be calculated by taking Q3 and adding on the rest of the interest for the year. Plugging in the numerical values for P and R, we get that William's ending balance is indeed $1,040.60. In the final quarter, his interest grew again, and in the end, he had 60 cents more than Dominic. While 60 cents is relatively inconsequential, that difference would grow exponentially from year to year. In fact, after 10 years, the difference would be over $80, and after 20 years, the difference would be over $400. Through working that calculation, we saw that the balance at the end of each interest payment was equal to the starting principal times 1 plus R over 4 raised to whatever power corresponded to that payment. We can generalize this and say that the ending balance, which we'll call A, after T years for an account with quarterly compounding interest, is equal to P times 1 plus R over 4 to the power 4T, since there are 4 payments per year. But since some banks may compound interest only twice a year, or perhaps offer it 12 times a year, we can generalize this formula even further. If we let n equal the number of interest payments per year, then the ending balance of a compound interest savings account will be as follows. Let's use the generalized formula in another example. Marlisa's savings account has $500 at the beginning of the year. Her bank pays 5% interest annually, which is compounded daily. What is her balance after 5 years if she does not deposit any more money? This is a bit of an extreme example because it's very unlikely to find a bank that pays 5% annual interest and compounds daily. Let's work it out though and see what Marlisa's ending balance would be. In this case, P equals 500, R equals 0.05, N equals 365 because the interest compounds daily, and T equals 5 years. Plugging all of these into the compound interest formula, we get that A is equal to P times 1 plus R over N to the NT, that's our general formula, and this is equal to 500 times 1 plus 0.05 over 365 to the 365 times 5 power. With the help of a calculator, we can determine that this comes out to $642. That's $142 in growth. Let's work through one more example. For the past 50 years, Mrs. Baker has been collecting interest on an initial deposit. Her savings account pays 3% interest annually and compounds monthly. If her balance right now is $8,946.62, how much was her initial deposit? This time we know the ending balance A, but we do not know the amount of the initial deposit P. We can solve for P though by rearranging our compound interest formula. Dividing both sides by 1 plus R over N to the NT, we can get P all by itself. Now let's plug in what we know. We know that Mrs. Baker has $8,946.62 as her ending amount, A. We also know that her annual interest rate, R, is equal to 3%, or 0.03, and that her interest compounds monthly, so N equals 12. Finally, we know that she has been collecting this interest for 50 years, so T equals 50. With the help of a calculator, we can determine that all this is equal to $2,000. So Mrs. Baker started her account with $2,000 50 years ago, and now it has grown to nearly 5 times that much. Now that we've used the compound interest formula to find both the ending and starting balances of accounts, you may be unsurprised that it can also be used to solve for the annual interest rate, R, or T, the number of years passed. While the compound interest formula is certainly more complex than the simple interest formula, you can commit it to memory with just a few minutes of dedicated focus, and the calculations are quick if you have access to a calculator. Einstein is credited with saying that compound interest is the most powerful force in the universe. With a little practice, you'll soon have this powerful force mastered. Thanks for watching and happy studying.